the Leavitt, the stars, and the Magellanic Clouds, and yes, that's me. And I guess I should be, like truth in advertising. Can I have the next slide, please? Or shall I click my own? Oh, click my own. Whoops. There we go. No. There we go. No, I'm seeing two screens. There we go. Okay. So this talk is inspired by, I'm a historian of science by training and all. It doesn't take a lot to get me to start talking about history, but this particular little historical video I'm tell you about is inspired by this great, big, vast blue cyanotype artwork, which is called Magellanic Clouds after Henrietta Swan Leavitt, and it's by the artist Leah Halloran. And let me just show you, because you really ought to see it by itself. That's what it looks like by itself. So why this one and why inspired? It's because working at Cepheid College for this last semester, this fall semester, actually for like the year building up to it, we have a gallery exhibit at our gallery on science and art, and this is one of the pieces in the exhibit, and I'll tell you a little bit. Here are the false pretenses, right? You think you're here for an astronomy talk. This half of it's going to be about an art exhibit, but you are people of broad minds, so I figured it would be fine anyway. So I developed this talk really because if we're not in astronomy, that's a kind of inscrutable thing to be looking at, right? So we needed a historical talk to tell you about Henrietta Swan Leavitt and Magellanic Clouds. And so that's this talk. So I'll tell you about that. Then I'll tell you a little bit more about the exhibit and the experience of building the exhibit. And oh my gosh, I've had such a year. But let's go first visit a little history. Let's hear about Henrietta Swan Leavitt. So there she is, Henrietta Swan Leavitt. As you see, her date's 1868 to 1921. So an appropriately vintagey looking photograph of her. She was a Massachusetts girl, family in Massachusetts, but she went to college, Oberlin College in Ohio, and then partway through, after having general sort of an education, for reasons I'm not sure entirely clear, she decided to move herself back to Massachusetts to what was called the Society for the Collegiate Instruction of Women, which was weird. It was a semi-official arrangement by which Harvard faculty members could deliver their lectures a second time for women in a suitably far away building on the other side of Cambridge Common. Not too close, don't want that. At the end, you got a certificate that said you've done, after you took the courses, a certificate that said, well, if you were a boy, you'd have a Harvard degree. But you're not, so you don't. Anyway, so she took astronomy there and got really interested and worked at Harvard College Observatory. Exactly how is not 100% clear. I mean, she was certainly a volunteer at the beginning from about 1891. She was actually paid from something like 1903, which I'll point out is a little bit later. And then she was paid until her death in 1921, not very much. They weren't paid a whole lot of money. But so that's just kind of like the background. Why do we care? What did she do? Well, she discovered the first Cepheid stars in the Magellanic Clouds, which we'll get to this in a minute, but not to give the punchline away. It was the first effective ruler for measuring distances at a galactic scale, right? You're astronomers, so you probably already are well aware that parallax, just the effect you get from being on a moving Earth looking out at the stars around you, that's good for distances with quite close-up stars, but especially then, technology of the 19-whatevers is just not going to get you very far into the universe. So, first effective ruler to measure distances across the size of our galaxy and somewhat beyond, and this was pretty impressive. She was posthumously nominated for a Nobel Prize, although they don't give the Nobel Prizes to dead people, so she didn't get it. Who knows? Maybe she wouldn't have gotten it anyway, but she was nominated. So let's take a little bit more of a look at how this work plays out. Oh, and by the way, stop me if you want any further comments or whatever, chatter about this or about anything else that grabs you more. Okay, so the big problem, and I would, from conversation with Ron at dinner, I mean, we all know it's a big problem. Do astronomers measure distances? How do astronomers measure distances well? It was a problem then, it's a problem now. The night sky just looks like the surface, that bowl over our head we always talk about. There are not obvious clues to the depth, to the distance, right? And as I was explaining this to students in my class, we're actually in a planetary science class, so they don't think about stars that much in my class. But you can start with a naive claim, right? If a star appears bright, is it actually bright? Or is it just that you happen to be looking at one of the really up close ones, which would be easy? I mean, for my student pool, really got to say this, it would be easy if stars were in any way standardized the same, and they're not. And they're not by just a little. I mean, stop and think about it. You may well know the magnitude scale of brightest stars are like a billion with a B. A billion with a B times more luminous than the dimmest stars. So, bright, as they said, I guess the phrase when I was first teaching is that faintness equals farness. No, that's not all you need to know, right? You need a way to somehow select some kind of standard candle so you know how bright a star really is, so you can then figure out how bright it looks. And so that's really the big problem. And these Cepheids, well, Cepheids are stars that vary in several parameters: luminosity, how bright they are, color, and radius. This is a simulation, but you tell me, is the longest period the slowest off and on cycle, or maybe I should say bright and dim cycle, is it the most luminous or the least luminous? The longest period goes with which, most or least? Longest cycle definitely goes with the most luminous in this particular picture. So that's a period luminosity relationship. And with my students, I don't get terribly deep into that. But nonetheless, any sort of relationship between how quickly it flickers on and off could be used in this case to give you a sense of how really bright they are, how actually bright the thing is. And then you can't say all Cepheids are the same, but you can at least say, well, the ones of a certain luminosity, or if I use a certain period, if I use the period to sort of figure out how bright it really is, and then I see how bright it looks, I can use that as a sufficiently standard candle. At this point, just to be historical for a second, astronomers were aware of other reasons the star could fluctuate in brightness. Their data was good enough here to see that the things of which they were most aware, an eclipsing binary, for instance, is not what a Cepheid was, because an eclipsing binary is bright, and then when one thing comes into the other, briefly and abruptly dimmer, and then it's sort of evenly bright. And Cepheids light curve is not that at all. So their technology was good enough to trace it a little bit better. So they could see that this was a special sort. Didn't know why. Didn't know what it was doing that made this happen. But phenomenologically, Cepheids are a particular kind of variable star, and you can identify them. Okay, so what's the Magellanic Cloud? Oh, and did you notice I cheated? I cheated right there by not even talking about essence and animation, right? We just aligned the whole question. Are those all going to be the same? Unless the animator wanted you to think about a cluster in the same distance, right? So I did cheat, I'll admit that. We'll get there in a second. Question?
I was just going to point out when I used to teach my students, I would talk about Oh, you have a 100-watt light bulb that's way far away and a 20-watt light bulb that's very close to you. I don't think kids know what a 100-watt light bulb and a 20-watt light bulb is.
No, they probably don't, because who's buying watt light bulbs? They're buying compact fluorescents, which are rated quite differently.
Shooting a camera phone, which is, those are, I think it's really hard to judge the distance on those.
Yeah. No, it's probably more obvious, especially because wattage is a really nice, on an incandescent bulb is a really nice measure of, I don't know whether they know that or not.
Yeah.
I'll have to think about that the next time I'm really trying to teach stars, if that happens. Okay, so my students being planetary science students, another thing they don't know are what are the Magellanic Clouds. So what are the Magellanic Clouds? Well, and they are what is pictured in the original Big Blue Beautiful Cyanide picture. They are, as you may well know, two small galaxies, which are satellites, not just neighbors of our Milky Way, but satellites in the sense that they move around our Milky Way. And they are 160,000 and 200,000 light years away, which, granted that our Milky Way is like 100,000 light years side to side, that's like another distance again. Respectively, the small one, the large one and the small one have about 10 or 1/100th as many stars as does our Milky Way. The key idea, though, is really this business about, here's how we solve the problem of, are these stars really all the same distance away? Because we have to know that about these Cepheids before we can actually calibrate a period luminosity relationship. So, and let's just get a picture of what that looks like. Because granted the numbers I just gave you for the Milky Way, when I say all at about the same distance, it looks about like this. That little cluster of stars is meant to be like about somewhere between, it's all at the same distance from the observer to like 10 or 20%. So that's what we mean by good enough all be at the same distance. They aren't all at the same distance, they're clumped, but that's certainly better than being mistaken with one of the stars over here, or maybe even over here, or way over there. So we can call them sufficiently similar in distance, and that's what the Magellanic Clouds mean. Magellanic Clouds being a clump of stars in space at a proportion sort of like that from an earthbound observer, as we all are, gives you something like that similarity in distance.
Are you making an assumption then about the size of the Magellanic Clouds? Because if they're, say, 150,000 light years away, but the whole cloud is maybe 20 light years across.
Your assumption, even more than about the size of the cloud, you're really making an assumption about the depth of the cloud. Is it ball-shaped, round, spheroidal, or is it pointing like a finger at you? For instance, are there two clouds out there, one here and one ways over there, your Earth, right, or your, at least our Milky Way, and they're actually aligned in the cosmos pointing towards us? And I'll tell you, that was a very William Herschel point of view. William Herschel being, let's see, we're in like the early 20th century here. William Herschel being like what, the late 17th, early 18th century? Yeah, late 80s, at least for the start. So William Herschel, like about a century and a half before, when you think of the extent of his work, I guess, he had no compunction about looking at things like the Magellanic Clouds and deciding that they really were a distribution of stars that was probably not compacted together, but all at some reasonable star-to-star distance. But the fact that it looked clumpy meant it was stretching out in space away from you. Think about this theologically. You're here in the universe, and there's a structure in the universe that points at you from here. And then over here, there's a structure in the universe that points at you from there. Aren't you special? I think that that was a very appealing idea from a century or so before, but not by the early 20th century. By the early 20th century, the assumption was that a cluster like that I think it's probably because people understood that there must be something gravitational going on, and that you should use that idea, and that therefore it was probably clumpy. And if you started in the universe with a long spread out structure like that, it would clump up. I think that's because he's more or less in panic than I am. I think that's what's going on. I don't think people accepted that you could have these weird elongated structures. People had a much better sense, really, of what the distances might mean, what the masses might be, how much the force might be, and that you had a very long time for things to move into some sort of structure of equilibrium.
Also, I think Copernican principle.
You also had the Copernican principle, and people have really internalized that. You're not supposed to be special. That's not the way we're supposed to do our science. So I think the Copernican principle philosophically and all these other bits of science, it's really as much that they're a roundish clump than that they are some kind of point-like device. So any more thoughts on that? Or whatever. Okay, all right, so all about the same distance. That's the good you get out of the Magellanic Clouds. So now let's go back and visit with Leavitt for a little while. Not long after she was in this ambiguous hired as a volunteer, can you use that phrase? Hired as a volunteer, started working on data at Harvard. Let's put it that way. Harvard had a lot of data from a Harvard College Observatory outpost in Peru in Arequipa. And Leavitt was doing essentially photometry, which is to say how bright things are, and looking at the images of, and they have lots of repeated images of, they were taking plates night by night over and over again over a period of time. It was a big funded enterprise. She was able to identify in the large and small Magellanic Clouds, in the course of her working on this over some decades, she identified and analyzed 1777, let's put it that way, stars that had the variable qualities of Cepheid stars. And assuming that they really were all at the same distance, I might not have known exactly what that distance is, but at the same distance, she came up with a period luminosity relationship in 1912. So she'd been working on this for about a decade by the time she published it, and the result of this is really pretty Cepheid stars as standard candles. So that's the accomplishment, and I just want to give you a sense of the sort of handmade, laborious quality of this. Because I think, well, maybe you people don't read it, but I'll tell you, if I'm talking to undergraduates today, they have no idea is as easy as this hard. How would you do it? The idea of photographic plates is a little remote to them, right? The idea of the computer is pretty remote. So this is a cute little animation by that I got from Harvard College Observatory, their outreach office. A filmmaker in their outreach office has done this, where he's taken apart the images that are the glass plate photos of Magellanic Clouds, two of them. And the way she would work is she would look at two of them. I think one is a negative and one is a positive, and you can superimpose them on each other and get a sense of where points have really varied from the night of one plate to the night of the next plate, because they don't precisely cancel out if something is varied. So the stars do. So anyway, this is a sense of how that works. You're going to see two stacked plates slide in, and then these are the plates she worked on. This is her handwriting, noting what she notes about these stars. So it just gives a sense that this is laborious. So the plates come in, and here she's writing, and by the time she's done, it looks like the end there. That goes by so fast. I just got to click that one again. I could spend all day sitting here clicking this, so stop me when I get to like round 6 and you're bored. mean, this was a lot of finding, a lot of identifying, a lot of work.
But luminosity, like 10.7 is the same scale we use today. Or 12.8, when we do zero.
I think so. I mean, it's very you can say a really significant telescope being hauled off to a distant location, but I mean, people did that.
Also, Cepheids are
Cepheid are all really bright. They are very bright.
Elements in different distance, something that's coming in at 10 to 1 magnitude. These are being braced.
Yeah, I mean, these enterprises were the first times people were identifying individual stars in a structure outside. They didn't even actually know that they were identifying. This is like about 1920, and I guess I should get to this in a minute, but I'll say it right now. Even in 1920, and this is more like 19 teens, people still hadn't decided that spiral nebulae were outside our galaxy. They didn't really know how big our galaxy was. They didn't know which things were inside it and which things were outside it, by which we're really talking about is something close up but not very bright or very far away, and wow, right indeed. I mean, you may know there was a great debate in about 1920 between Heber Curtis and Carlo Chaplin. I think the American Philosophical Society, which was really our spiral nebulae internal structures in the Milky Way, or are they island universe outside the island of our universe, and that means our universe is smaller than not the whole universe, or when they say our universe, what you mean is a collection of stars we recognize in the Milky Way. Is that really a comparatively small region with other things going on outside? So they didn't really have size. I think they were aware that they were looking at something that was exceptionally bright, exceptionally far away and exceptionally bright, but that could be so many orders of magnitude that I think they really didn't yet quite get that. So anyway, that's the kind of work that Leavitt did. And let me click forward here and just sort of, there, you see it in writing. For the first time, you got a ruler to measure, if you employ Cepheid this way, for the first time you have some kind of a ruler to measure these distances. You still probably need to normalize it, but you've got it. And this eventually will give you the size of the Milky Way, the fact that the Magellan clouds lie outside our Milky Way, and then ultimately the idea that if you can see a Cepheid in something like Andromeda, our nearest neighbor spiral, that you really identify that as an external galaxy comparable to our Milky Way. So since I'm telling this story largely in pictures, let me show you this picture, which I love. In fact, I love the composite of this picture. I mean, there's Andromeda, gorgeous Robert Gendler photograph. But here, Edwin Hubble, 1923, Carnegie Observatories, 100-inch telescope. You can go to Carnegie and they'll display this photographic plate. And it is Edwin Hubble's 1923. He's looking for novae in Andromeda. See the end? See the end? Oh, I can't reach it, but see the end up there? And then notice there's crust at the end. There, it's the Cepheid variable star. And that is Hubble galaxy realizing that he's found a Cepheid in Andromeda. And between the decade between Leavitt and that work of Leavitt and this work of Hubble, there's been a lot of calibrating going on. So he can really identify the Andromeda Nebula as a spiral galaxy. And I mean, there's lots and lots of history about spiralness and what people thought that meant, and when they thought maybe that's what we had, had and stuff like that. Once upon a time, I probably could have given that to you blow by blow, but I don't even want that tonight. Just by way of contrast, I mean, look at, so this box here is the takeout from that section at Andromeda. You can kind of trace all the bits. If you look at the variable, that's the rectangle up at the top of the somewhat larger rectangle, and that takeout just shows you what that looks like in you just see. So boy, have we come along with this.
Real quick question on this. It looks as though the star that is in the circle in the Hubble Space Telescope, is that the same as the variable star?
That is Hubble's Cepheid in Andromeda. Yeah, it's kind of amazing.
And it also kind of gives you a sense of what you're looking at there, because even that patch of M31 that you're looking at, right, there's probably something like 10 billion stars in that patch of sky. And there are maybe 5 that are as bright as that. So
Yeah.
so Cepheid really are exceptional bright stars, which is why they're so useful.
Yes.
I think that Polaris is a Cepheid.
What's the typical period for these seconds? Are you gonna get to that?
Days to week.
Days to week.
Days to week. I mean, I suppose for you folks, I didn't really for my planetary people, but what's a Cepheid doing? A Cepheid is a star that is evolved off the main sequence, becoming a giant star, or even a supergiant star, but it's in a region that's described on the Hertzsprung-Russell diagram as the instability strip. And what happens is that it's just at, you can jump in if I'm saying it's right, because I haven't taught stars for several years. It's not at flat. So let me see if I can get this right. It is at such a temperature and pressure and degree of being held together by its own gravity that its temperature fluctuations induce opacity fluctuations. So you can think of that as kind of like a valve that flips on and off. And here's how it goes. You've got the star, and its outer layers are a little more opaque than normal or than average, and it's a little smaller than average. Those outer layers being a little closer to the heat source, well, they warm up and the whole thing fluffs up a little, and as it warms up, it expands and it's trapping the light energy, and then it gets warm enough that it becomes a little more transparent, and that flips the valve. The light escapes, the heat escapes, and it's been puffing up, and then it collapses down again. And so it's sitting here kind of squeezing in and out, if it will. It's expanding and contracting. It's being opaque enough that radiation pressure is driving the outer layers even further out, and then it gets a little more transparent, and that lets the light through, and then it's not as much radiation pressure, and gravity takes over a little, and the thing falls in again. So it's basic, and the animation I showed you, while this is happening, is a complicated cycling of its diameter, its brightness, and the color, which is a reflective of its, which is radiative of its temperature. Reflective works in English grammar, but what it's really not doing is not reflecting, it's radiating different colors based upon its temperature. So it's pretty complicated, and 1923, they didn't begin to understand how stars function enough to do that. So they didn't know what they were looking at. That would only begin to come along in like 1926, when Arthur Stanley Eddington sort of realized quantum physics isn't happening, and starts thinking about how you can apply that to the internal radiated and gravitational the structure of stars based upon the fact that they're held together by gravity, but they're puffed up by radiation, by light, by heat, and you've got a hydrostatic equilibrium that may oscillate like a Cepheid, or it may just sit stably for an extended period of time. They get main sequence stars, and then later they pop up in giants. So, oh, well, they didn't not have that. Great. Graduate school friend of mine calls what they had in 1923, and they were edging towards quantum physics, and she called it Beta in the Woods quantum physics, in the sense of it's got some sense that there's something to be done here, but it is not quantum physics in the modern sense. But therefore, it's limited to what you can expect it to do with actually telling you how a Cepheid works. Two questions.
My question is, how do you know which Cepheid is Cepheid rather than kind of variable?
Oh, that's because if I graphed a variable that was like varying because you have one star here, well, two stars in orbit around each other, and they're brightest when you can see both of them and dimmest when one eclipses the other. That light curve would be sort of like maximum brightness with some dips when these so-called eclipses are happening. So it would be a shape that goes along flat with a little hole, along flat with another hole, along flat with a repeat of the first hole, along flat with the second hole. Cepheids light curves are curvier. They're not a sine wave like an ocean wave, but they're sort of distorted ocean wavy shape.
And so they all have similar light curve.
They have this, yeah. It's the similarity of the light curve that tells you you're looking at comparable beasts.
So when Hubble was looking at what he thought was a nebula, he was seeing a light curve that he thought was a nebula, and then he realized it was a Cepheid light curve.
Yeah, because you need to have a bunch of different plates. There need to be more than one photograph, and you need to see that thing flickering brighter, dimmer, whereas the novae, they aren't there, and then suddenly they're there and they stay for a while. And then they just go away.
It's over a period of time.
Oh yeah, all of that is.
Oh my God.
It's sort of amazing the extent to which people put in the effort to take observations in a standardized way over and over and over. So, I mean, comment on the data that's been preserved. This one, but also the Leavitt photographic plates I showed you. I mean, this one's still there at Carnegie. Those are all still there at the Harvard College Plate Stack Archive. They've all been digitized in case like the building was down. But they are, of course, most precise in the original form without any digitization. People still do sometimes refer to them for long baseline observations where you'd really like to know the condition of that astronomical object more than 100 years ago. And I don't know, I mean, I know that as recently as the 1990s, the plate stacks in Geneva Lake, remind me of the telescope, the one outside Yerkes. The Yerkes plate stacks were still in regular use by people who were just going in and just digitized yet. Literally just going in and looking at the historical plates and figuring out, I mean, I knew someone who was working on proper motions of star and globular clusters to get how the stars orbited globular clusters, and they were just letting her take the plates and measure how things moved on the plates. It's kind of amazing that, I mean, that's a lovely pre-digital revolution moment for me. That here she was, 100-year-old plate, she was a graduate student. They let her have these things to use because they didn't say use the digital one, Miss Schweitzer, you can only use the digital, because there was the digital one, so you're a graduate student, be careful, here's the plates, use it. That's our historical basis for seeing how fast things change, because that's what they're there for. Now I think they're mostly more historic relic, these flex plates. But sometimes they are there for research, even that, I think. And nobody wants the buildings to burn now. The other pockets.
Oh, well, you kind of answered my question, although it still just stuns me that somebody took the time to study as close as the observation that it would take to find those novae.
Astronomy was that level.
Yeah. But my follow-up question is, Cepheid, does that have something to do with Cepheus?
Yes, the tight one of it is in the constellation.
Delta.
Thank you. Now, well, maybe sometimes, but not when people are looking at me. Okay, well, let's see what we have next. Where'd my cursor go? Ah, there we go. Okay. All right. So, okay. So that's mostly there just because I really hated not to have just Andromeda in its full glory. So that was the prettiest Andromeda I found. Obviously more modern, it's HST. So that's what we look like. I mean, we can't see what we look like because we can't see our own galaxy. But as near as we can do it, that's what we look like from the outside, except none of us will ever get outside to look at it.
And I just had a quick comment. I know a couple of people who were involved in rescuing the Palomar photographic plates because they were stored in Caltech, and Caltech wanted to use that space for something else, and they were going to destroy them. And a few people got together and said, "Don't destroy them." And they found a place to move them to.
That's a remarkable thing. Being originally trained in historic science, it is a remarkable thing how often, but this probably applies to many other fields, how often people are willing to throw out their history because they decide it's not going to be useful anymore. And some of these things are so obviously historic. Others of them, yeah, they probably will for long baseline things sometime get used. It's hard to predict which ones of the plates. So that's a problem because it takes up space to store this.
What are the odds that some of those foreground stars are Cepheids that might think about it and
Oh, I'm sure there are, but not enough. I mean, you just have to sort of take it and say there's going to be some foreground junk. That's what stray data that doesn't picture.
But that's gonna be, well, again, M31's a pretty small chunk of stuff. You're not looking right through the middle of the Milky Way there, you're looking way out of the plane, so you're not looking at very many Milky Way stars. They're gonna be huge, and of course the Milky Way stars are gonna be, 10,000 times brighter. So it's going to be it's not like it's going to be a factor of 2 difference. It's going to be wildly different. So the foreground stars in that picture are like standard main sequence stars. Because if you put a Cepheid in that picture, it would blow out everything else in our galaxy. Right? It would be as bright as if there was.
So sometimes
there's
Probably Delta C.
I'm going to click forward. I'm going to stop and have some editorial comments here. I've spoken to you folks any number of times. You probably already gathered things like women in astronomy are really my thing. I just want to point out that these women at Harvard College Observatory, there's Leavitt. Right there, she's standing with Annie Cannon, who is the person in charge of the Women at Harvard Observatory, right? Well, what the observatory had as soon as astrophotography happened, taking pictures, taking photographs through a telescope, what they had was a data deluge. And this is sort of a problem. Data analysis is neither observation at the telescope at night, the heroic thing astronomers do, nor is high theory, which is kind of so heroic thing to do if you like high theory and are highly mathematical. Data analysis is grubby, low prestige. It has to be worth any value at all. It has to be done efficiently, meticulously. What do you mean cheap labor? I mean, there's this phrase about Henry Pickering, who was the director of Harvard College Observatory. So what did he really? And my version of it is cheap labor. The edgier version is women. But it comes to the same thing, right? That's what cheap labor was. I would say this might be marginally better than generations before in Britain, where Greenwich Observatory made use of cheap labor, by whom they frequently meant orphan boys, because it's, after all, much nicer than most of the other orphan boys will be doing. Remember your Dickens being taken off to sit there be a scribe and calculate is probably better than sweeping chimneys. Anyway, so these women, oh, and the nice thing about having a photograph is that the work can be done daytime, chaperones, in an office, very virtuous, right? You can't tell what's going on in it. Most of the examples of women we have in this and earlier eras who did serious telescopic astronomy were either doing it in some kind of a familial context or a college context, where they, again, I mean, they had a certain level of assumed protection. They worked out alone at night, right? So there's a lot of sociological stuff going on here. These people, these women, they were, as I say, not paid much. What they did in addition to positional calculations, which was sort of the traditional calculator stuff that was data analysis, they also did spectroscopy and photometry, and I'm going to go out on a limb here and tell you that they changed astronomy into astrophysics. Because without this level of this kind of data, you don't move astronomy into the kind of ability to explain what's going on in stars in a physical sense. Now, were they all the astronomers who did this? Some were, some weren't. Several very important ones were. I'm going to tell you a tiny bit more about Cannon in a minute, but so also Antonia Maury. I have been told her expression on her face here explains how badly she got along with, for instance, Cannon here, who was she was even possibly more meticulous, insufficiently efficient. Anyway, so these workers, yeah, this is kind of what they did. I just wanted a word or two on Cannon because she's actually the most famous of them, and we'll explore that real quick. Annie Jump Cannon. Notice her dates are not that different. She started at Wellesley College. She actually was a student of Sarah Frances Whiting, who was a full-on physics professor at Wellesley College. In order to get better access, because she knew liked astronomy, and there was a limited amount of astronomy that could be done with the Wellesley equipment, she also started. Now, what you say is it says she went to Radcliffe College in 1894. I think it's still that arrangement where what did we call it? The Society for the Collegiate Instruction of Women. Not really a college yet. I have read that she was employed as a Harvard computer from 1894. What's it? I think when you read this stuff, I would love to go back. Like, was she really paid? Was she really employed? Was she? In the end, both of these women were paid, and I'm not sure if maybe Cannon was paid a little earlier. What she did was classify stellar spectra. So here she is, much later in life, posed picture. Light comes in from a window, reflects up here, shines through the glass photographic plate, which is held in this thing at an angle, and she looks down on this field of spectra and classifies the spectra. We may have to come back to those numbers because I want to hop ahead and show you what classifying spectra looks. Now, maybe I better. Now let's hop to ahead. When I say classifying spectra, that's what the plate is like. Every one of those smudges is the spectrum of a star. So you know the star field, you go to the spectrum field. And Cannon was set the job, Maury was first, and then Cannon, of figuring out some kind of a simple enough classification system that it was useful. So you know OBAFGKM, right? Hers. And nobody would set out to classify anything OBAFGKM, right? A, B, C, D, E. It's just that they don't turn out to be like any C's or D's or E's. Nature, it turns out that was a mistake. Nature doesn't really do that. But the other thing is, Cannon's real contribution was kind of to winnow down to the OBAFGKM we recognize now, and then to realize that if you focus on things like the hydrogen lines, show up particularly well there, and then they fade out in the higher letters, so to speak. you can actually have a sequence that clearly there's similarity between one and the next, and so they have to go, nature somehow gives them to you in this order. And so she gave us that sequence, and that is nowadays we would recognize it's associated with the colors, which is to say the temperature of the surface of the the apparent surface of the star, and it tells you how hot the outside is. And so that's one of the axes on the Hertzsprung-Russell diagram, which is the way we organize what stars are. Yeah. And you only have fairly dim ones of the higher letters like M stars and K stars, but you get only really, really bright ones of the O's and B's. So there you go. That's the kind of work she worked on. Forgive me for clicking now backwards to again, because it's just phenomenal. She personally and individually classified more than 350,000 stars in her life. And people kept track of things like she can classify 200 of them an hour. Looking at those smudges and classifying 200 an hour. I once read a quote where someone asked her, well, how do you know? And she said, well, I know them like I know the faces of my friends. Faces of my friends, as well. How do we know 200 stars an hour? It was a pretty regimented workplace. They tracked when everybody came in and sat down. They tracked where they started, how far they got, and they tracked how many hours they worked, and then they all got up, and then they all went and they spent 15 minutes having tea over here in this other room. Not to get tea on the plates. And then they all marched back to the next shift. And this is a very organized enterprise. So we know that accuracy. A doctoral advisor was of an era that he knew some of the people who were young students sort of at the end of her era. And what people who were young students used to do when she was about that age was go back and say, Miss Karen, I didn't make a mistake on this one. I want to hear what you said. It's just kind of for the little blind. Always classified. That's the story. That's accuracy. Maybe more accuracy is the whole enterprise worked. It wouldn't have worked if it weren't accurate. Okay, so 1925, first woman to receive an honorary doctorate from Oxford. Oh, there's just a random set of first wonderful things. I put that on because I just have always loved that picture, the expression on her face. I would bet of all of those awards, she probably most cherished being elected a member of the Royal Astronomical. I would bet that meant most to her. In a modern sense, the American Astronomical Society's Tandon Award is named in her honor, and it's given to promising young women in astronomy. And all of them. And that's only some of the ones. Oh, she's pretty remarkable, I think, as well. Okay, back to what motivated me in all of this image. So there's a little bit of history, and I was telling it to students because we have these things in our this thing in our gallery at Cepheid right now. It's part of a larger series by this artist, Leah Halloran. This is not our gallery. This is, I think, something else in the LA area. Halloran has done a whole series of these monumentally large cyanotype prints of contributions of women in astronomy since antiquity. And she goes back to people like Hypatia of Alexandria. And there's lots and lots that you can read about it. They are really remarkable works because they are just, there's something about there being vast blue thing that just feels silent. At least I think it is. If you go to her website, you can see pictures of her making. She hand paints the mask that you put on the cyanotype treated paper, which is treated with cyanide and other things, and iron cyanide, something or other else. But that then masks the light and take it out in the sunshine, which is a very artisty way of relating to the sky, I think. And then the cyanotite, where it is exposed, it dyes this dark blue. So it makes these amazing pictures. And so this is her sort of tribute to the women of astronomy. And it's got some attention, right? Dave and I were walking down this hallway between Terminal 2 and Terminal 3 at LAX as we were coming back from summer. And we're walking along from that direction. And we were walking, and I first saw the first one appearing on the wall, and I guess they screech so loud, exactly. But you know, they're very arrived all four airports having interesting things to look at. And woke me up even after my horrible long flight. So why are we doing any of this at Cepheid? What do we have to do with this? Many of you are Cepheid people one way or another. So I want to invite you to what we're doing at Cepheid until November 18th of this year. So you've got a few more weeks. I mentioned this exhibit on science and art. We have this exhibit on science and art. It is not huge. You're seeing about half the exhibit in those two views, and then we've got some other roomlets. And a group of faculty joined together with our exhibit curator. Our museum doesn't have a permanent collection. It just has temporary collections that are somehow exhibitions, which are somehow temporary exhibitions, which are brought together to showcase something that we feel matters to our community. And for some years, we've wanted a science and art one. And so we're having it this year. We have math and art in the spring. And a group of us, guided by our curator, looked over the art of maybe 50, 70 artists that Rebecca Charlick, our curator, she's the professional, identified as being interestingly related to science and art, and we were allowed to pull together a wish list based upon things we thought that would be interesting. You know, the amazing thing, they all said yes. Maybe with only a few, this logistically wouldn't work. Artists turn out to be really interested in bringing art, not just to the galleries of Gallery Los Angeles, right? But out here to the Inland Empire, where there are not so many art galleries, and they are allowing us to display these amazing pieces. So you are absolutely invited to come take a look at this. I'm just going to tell you about a couple of my favorites, obviously. The cyanotite of the Magellanic Clouds is my top favorite, right? But some of my other favorites, just to show you the diversity. This one is a watercolor. Large scale, not it's blown up in here, but it's for real, like about this big water. By David Goodsell, who does illustrations of cellular and viral structures. Do you remember what you know that virus? Okay, that's what it is. It's a COVID viral particle inside what's the phrase for a respiratory droplet. And he's capturing the fluid surface controlled by the thing controlling the surface of the respiratory droplet is the same surfactant that is in your lungs. If you did not have a surfactant in your lungs would be stuck together, damp, and they wouldn't be able to open up to get air inside. The biologists filed about this, so I told me a lot about it. They're gorgeous, they're detailed, it all means something. He describes it as scientific illustration first and art second, but it's amazing. We've got several of his. Also micro, but in a completely different train of thought, is an artist who makes these gene zines, where she takes the microbiome of polluted water sources and puts droplets of it onto the zine and encourages people to rip that out and drop it in some other polluted water source with the idea of sharing genetics of organisms that have learned to get by in tremendously toxic ways. That's interesting. I did no idea that artists did that kind of thing, did you? Other things, here's someone who makes a box of sugarcane, a paper-like substance based on sugarcane fiber, in which she includes petroleum-based plastic particles that she used from New Orleans. And are those bits of jazz trombones, or are those piping for oil infrastructure? I don't know. You tell me. And do we have anything? Oh, and here's our artist who takes amazing videos. There's like a 20-30-minute video of ants, leaf cutter ants, this little dark guy here, carrying things and operating with what looks to us like intent, but our ant specialists assure us they don't have intent the way we do. Carries pieces of leaf, and she's photographs them doing this, and it is so entrancing. I could sit through that loop like 3 times over. So that kind of stuff shows up in our exhibit. And then there's lots of programming we use in college. So we do programming, we have receptions and artist visits, trainings, and workshops. Decide how to get your students into the art exhibit, what you might give them for an assignment. This is so interesting. And then we even have a play reading. There is Sheila Malone, one of our theater professors. You'll see Dave in the far corner over there. And typecast is the older female astronomer. It was a play reading. We didn't really act it fully, but 2 theater students and I read a play called The Astronomy Burlesque Play. It sounds rather, maybe a little juicier, actually. Like, really a play about science and gender and careers, but also about astronomy and art and seeing. Right? The artist at one point says, how did you guys get to run away with the word, you astronomers get to run away with the word seeing? We artists, we really want that word. I mean, like, how's your painting of a naked lady? Oh, really great seeing. And the astronomers are saying, oh, we're going out tonight because it's good seeing. So it was a play that, frankly, fascinating to do because what the playwright said, and so many conversations about women with other women of my era and older and younger in astronomy for the last 40 years of my life, and everything in that play is something that one or the other of us have for real said to each other about our lives. So what is this whole fight? So that gives you a sense of what it is, and it's obviously you're invited. James College Gallery is freely open to all, and parameters later. What do we think this is having? What effect do we think this is having on like faculty and students? It is the most, I've been teaching astronomy at Cepheid for 20 years, and it's getting to be a little the same, right? I mean, it changes, there's new things, but it's getting to be a little the same. The idea of working with other people across the college, artists, theater professors, other science professors, some of the people who just randomly come in and talking about what is it, the 2 different ways of looking at the world. The sciences, me, astronomy, but also like the physics and the biology and the geology and the geographers. We have our way of looking at things, and the artists, they have this way of looking at things that isn't science, and yet we start talking about things like identity. What does it mean to be an individual? Or classification, taxonomy. What does it mean to classify stars and galaxies or something? What does it mean to classify something in art? And it just made me think more deeply and more differently. I swear to you that I am twice as interesting professor as I was last semester. I really am. I hope my students see it, but I know I am. One of the things we did, talking about classifying. Well, first we had them classify random, not group, I mean, Okay. Classified, but they're not biological students, so they don't really know that. Is there a way to classify fasteners? Or can be? So we had them talk about classifying and then see what we gave them to classify. It's fascinating. Did they come up with the Hubble tuning fork classification for galaxies? No. You know what they came up with? They came up with things that are far more like, when did you last actually read about galaxies as, you know, the tightly woundness of their arms, the Hubble, classic Hubble ways we're supposed to classify galaxies? No, you read back to the Starburst galaxy. Is it got full of star forming region? Does it have H2 region? How bright are they? They were really not going by the standard obvious. Now it makes some sense, right? Because they were getting Hubble and Webb pictures where color is evident, whereas in the old ones, the people like Hubble used to classify galaxies, that stuff wasn't there. They were dim little murky things, no color at all. But these students were just coming up with statements that were wildly different from what I expected them to say, and certainly not wrong. Fascinating. Fascinating. So there are your parameters. Free and open to the public. Visitor hours. You gotta go. Some hours. I think Jada handed you all the exhibition. Even. And there are even some things like music and art on Monday, November 13th, programming on the back. I have always believed in interdisciplinarity, the fun of thinking in other regions you don't normally think about. I have had more fun with this. Boy, if I retire next year, I'm going out. I know. So, anything left? Thank you. Please visit the exhibits, unless you'd rather go back to the hours.